Welcome to this second lecture in the series on NMR spectroscopy. What we've done in lecture number 1 is that we've looked at some basic terms and recapitulated all of them with respect to NMR. We'll be continuing that to different types of NMR spectrometers and also concepts which are very important and crucial to understanding an NMR spectrum, which is chemical shift. What we've already done is that we've looked at the concept of nuclear spin I, and we've said that all those nuclei which have a non-zero nuclear spin will exhibit an NMR signal or an NMR spectrum. But what we've also done in the previous video is that we've used the energy associated with the radio frequency radiations and the applied magnetic moment replaceably. So we've talked about NMR spectrometers which are 60 megahertz in capacity or 100 megahertz in capacity. Now, what I wish to emphasize on is that the frequency of the radio frequency radiations and the applied magnetic field can be used replaceably in case of NMR. And that is possible because of this particular relationship that exists between the applied magnetic moment B naught and the energy separating the two nuclear states, spin states of the ground and the excited nature. Now, this graph tells us that there is a linear relationship between the extent to which the energy separation is there between the ground state and excited state with that of the applied magnetic moment. And therefore, in the last video, if you had checked out, a 60 megahertz instrument operates at an external magnetic field of about 1.41 Tesla. So when you incident a magnetic field of 1.41 Tesla as the field strength, then the energy separating the ground state and excited state for a proton happens to be about 60 megahertz. And as we'll come to realize in parts ahead in the video, we'll be discussing different types of spectrometers, and in that you would see that in principle you could either hold the radio frequency radiations a constant and sweep the external applied magnetic moment so as to result in a resonance criteria. That's one way to do it. Or another way to go about it would be to hold the external magnetic field a constant at the nucleus and sweep the radio frequency radiations from a certain finite frequency to another finite frequency and check at what frequency resonance criteria is being met. And you would see that the first type of spectrometers are more common, whereby the external applied radio frequency radiations are held constant and the magnetic moment is swept over a small range so as to result in resonance criteria. And that's why this particular notation has stuck, whereby we call a certain spectrometer as being 600 megahertz, 100 megahertz, 60 megahertz, and so on. So what we'll be discussing in this particular video is that we'll be looking at the concept of chemical shift and shielding, which is one of the most fundamental things to understand so as to be able to make sense of NMR spectra. We'll then be progressing on to different types of spectrometers, and two of them we'll be discussing in this video, which is continuous wave and Fourier transform NMR. And towards the end of this video, we'll be looking at a concept called as peak integration and how it helps us in interpreting an NMR spectrum, which is most commonly the proton NMR spectrum that uses peak integration. Now let's try and understand this very crucial concept of chemical shift and shielding. What we've done so far is just to understand whether a certain nuclei will be NMR active or inactive and what would be its magnetic susceptibility so that an applied magnetic field would displace the energy levels of its ground state and excited spin states by what extent, so that we can theoretically predict what frequency of radio frequency radiations would help in transitioning from the ground state to excited state. How does that help us in structure elucidation? Like, say for example, if we have a molecule of ethanol and I'm probing based on all my theoretical principles the transitioning frequencies and the external magnetic moment that is capable of transitioning the proton nucleus from its ground state to excited state. Now I have three different types of protons here. I have the methyl protons, methylene protons, and the proton connected to a heteroatom, which is oxygen over here. Now, is it possible to distinguish between these three types of protons as they transition from ground state to excited state? And the answer with respect to NMR spectroscopy is a big yes. And that's the reason it becomes one of the most versatile tools to do structure elucidation. Now, how is it that their resonant frequencies become different, or how is it that in a spectrum we are able to see the three peaks appearing at different resonant frequencies, is something that we'll be discussing in the concept of chemical shifts. Okay, so the idea in NMR is that when we apply an external magnetic field B naught, there is splitting in the degeneracy of the spin states in the nucleus to a lower ground state and a higher excited state. And provided we apply a suitable frequency of electromagnetic radiation, in this case it happens to be a radio frequency radiation, you can have transitions possible from the ground state to the excited state. Okay, now how does the local environment around the nuclei affect this separation of energies is what is going to be dealt with in the concept of chemical shifts. Okay, so every nuclei also has some electrons that are in circulation around the nucleus, and these electrons, also being charged particles, will be affected by an external magnetic moment, and as they come in under the influence of this applied magnetic moment, they also perform some circulatory motion, and these circulating electrons in the valence shells will result in an induced magnetic moment due to the circulation of these charged particles. The induced magnetic moment is in the opposite direction to that of the applied magnetic moment, and therefore what is experienced by the nucleus is a sum of the applied and the induced magnetic moment that is generated by the electron cloud or the electron density which is present around the nucleus. So larger the electron density around the nucleus, lesser will be the effective magnetic moment that is felt by the nucleus in comparison with another nuclei that doesn't have a large electron density around it. And that's represented in this particular figure of 3.10 here, that the diamagnetic shielding of a nucleus is caused by circulation of valence electrons, and the circulation by itself is set up due to the applied magnetic moment B naught. And these circulating electrons will generate a magnetic moment of themselves, and this magnetic moment is something that is going to oppose the applied magnetic moment B naught, and that's what results in slight differences in the energy levels between the ground state and the excited state from one nuclei to the other, and that's what results in non-magnetic equivalence and can then result in the peaking appearing at different frequencies at which there is resonance criteria that is being met. So if we consider the electron densities around each of these nuclei, you can distinguish the three different types of nuclei as A, B, C, which should show peaking at different characteristic frequencies. Having said that, it should also be noted that the difference in the frequencies is not large, and the difference itself happens to be of the order of just a few hertz. Okay, when the external magnetic field that is applied is to the tune of about 60 megahertz or above. So if we translate this in the form of a ratio, it works out just to a few ppm or less than a few ppm difference that results due to an enriched electron cloud around the nucleus or decrease in the electron density around the nucleus. And in case if you're wondering that whether such a small difference really makes a difference, the answer is yes, that small difference is enough so that we could play detective on the molecule. So what we've discussed is that based on the local environment around the nucleus, its resonant frequency is going to be affected, in which it can either be pushed a little upfield or downfield. These concepts will be expanded a little further through the video. But what is quite important to look at is that the difference between these frequencies is not very large, and we established that towards the end of the previous slide, wherein we said that the difference between the resonant frequencies are only of the order of certain ppms. And if you get such a small increase or decrease in the resonant frequencies, then it will be very difficult to make a measurement of the absolute value of differences between the frequencies. Fortunately, judging the absolute value of differences in the frequency is not a prerequisite to do structure elucidation. So one that we establish here is that absolute values of shift is not needed. We just need a relative shift, and it should be relative to that of some standard. So if we also run a standard internally along with the sample that requires to be analyzed, it's enough for us to measure what is the difference between the peak position of the standard reference compound to that of the various nuclei present in the sample. And this is what is mentioned as a chemical shift. However, this shift values also are not independent of all factors. Now, it is important that a chemical shift value should be characteristic for a certain nuclei, and it should be able to help us in doing some structure elucidations. However, if minor changes in the experimental design change these values of shift, then it will no longer be standard, and if it is no longer standard, it can't help us in doing structure elucidations. Now, what was observed was that with the external magnetic field, the shift values also were seen to differ. So to the extent of an increase or decrease of the field strength, you will get a difference in the shift of a certain peak from that of a reference material. Now then that means that it's no longer a constant, and if at all you record the same sample NMR at a 60 megahertz capacity, or you replace that and make the NMR now 100 megahertz, you would see that the shift in between these two records would not be the same. Now that poses a problem because we want the shift values to be absolute, should be independent of the applied radio frequency or the applied magnetic field, as we've already discussed that these things can be looked at interchangeably. So what was done was a value called chemical shift was defined, which is nothing but a ratio of shift of a certain signal from that of the reference in hertz to that of the operating frequency of the NMR, and that operating frequency has to be in megahertz. So if there is a shift in the signal by about 72 hertz, when we incident or when we use a 60 megahertz instrument, then the chemical shift value will be defined as 72 divided by 60, and the final value will be given in units of ppm. And that ppm is something that can be easily conceptualized, because parts per million is 1 part in a million parts, or 1 part in 10 to the power 6 parts. And since megahertz here is 10 to the power 6 times that of a hertz, this quantity definitely works out to a ppm unit. The reference compound that is used to measure shift with respect to is this very famous compound called tetramethylsilane, or TMS, and this TMS is used to give an intense signal at an arbitrary delta value of 0 ppm. So it's arbitrarily assigned that the resonant frequency of TMS be taken as 0, and the shift of a certain nucleus in a certain sample be measured with respect to the deviation it holds from that of the 0 ppm value, which is marked by the TMS as an internal standard. This is a typical block diagram of a continuous wave NMR spectrometer, and it's called so because there is a radio frequency oscillator source that provides a 60 megahertz or some constant radio frequency radiations to the sample, and then it moves on to the RF detector, which helps in understanding whether there is an absorption that's taken place or not. And what is done is that this sample, which is spun due to some reasons we'll come to, is kept under the influence of a magnetic field here, whose north poles and south poles are designated. And this magnetic field strength is variable within a slight range of above and below 1.41 Tesla, plus or minus a few delta ppm. That will help in getting all the different nuclei of proton in that particular sample to come into resonance as we sweep the external magnetic field from some finite value to a certain other finite value. The spinning of NMR tubes is done so as to result in a homogeneous field around the sample, and that there should be no inhomogeneities of the magnetic field strength that is exhibited by each and every nuclei in the sample. And such type of spectrum which results from a continuous wave NMR spectrometer is called as a frequency domain NMR. Modern NMR instrumentation consists of a Fourier transform NMR that is an advancement from the continuous wave NMR, in which a pulse of radio frequency radiation is applied to the sample over a very short period of time of a very high intensity. And once the radio frequency radiations is cut off, you get some range of frequency that goes and hits the sample. And this narrow range of frequency which is available to the sample helps in exciting all the nuclei, different types of nuclei that is present in the sample. Once they go to an excited state, all of them relax to the ground state, and this relaxation happens with characteristic emission of radio frequency radiation. That is a function of the difference between the energies of the ground state and excited state for that nuclei, and as it comes back down, it will emit some characteristic frequency of light. And this decay is also called as the free induction decay. And this free induction decay looks somewhat like this. If at all you look at an FID file of a certain NMR that is recorded in the FT NMR. Now, what the FT NMR does is that it separates each one of the waves which have interfered together to give this pattern from the different types of nuclei that are present in the sample. And once it separates the different types of nuclear FIDs, it converts the time domain signal into a frequency domain signal. And that's done by Fourier transformation. Thankfully, we don't require to go through the detailed mathematics involved in Fourier transformation, because modern NMR instruments come with computational facilities, and the computers have softwares which help us in converting the FID files into a frequency domain file. Now, what are the advantages of using FT NMR over continuous wave NMR? The first advantage is that FT NMR spectrometers are highly sensitive as against continuous wave NMRs. Also, the signal to noise ratio is improved because the number of scans that can be taken over the same period of time is much more in case of FT NMR, because a scan is complete in a very short span of time as against a continuous wave NMR. And the signal to noise ratio can improve as the number of scans goes on increasing by this formula, which states that signal to noise is a function of root over number of scans. And as we take larger and larger number of scans, we can go on improving the signal to noise ratio. Nuclei that are less abundant can now be probed, and useful information can be gauged because of development of FT NMR. And the reason why we have good amount of interpretable data from C13 happens to be because of advancements in the FT technique for NMR, because C13 nuclei is relative abundance is less than 1% in nature, and therefore because it is very less in its abundance, we require a highly sensitive instrumental design so as to be able to probe this nuclei. Another advantage is that nuclei which are not strongly magnetic, and here also we can cite the example of C13 nucleus. If you go back to video number 1, we had defined a certain parameter for every nuclei called as a gyromagnetic ratio, and this gyromagnetic ratio happened to be only a fraction for C13 as against H1. So that means that a C13 nuclei is not as strongly magnetic as an H1 nucleus is, and despite that limitation you can get useful information from running a C13 spectra based on FT technique. Routinely in an H1 NMR spectrum, you would see that the information is given as 2.3 delta ppm, 3H singlet, and so on and so forth. Now let's leave the singlet and the multiplet or the spin multiplicity at bay for now. What is important for us to know is that every time there is a signal that appears in the H1 NMR spectrum, we are in a position to know the number of nuclei that contribute to that particular signal. And this is possible in case of H1 and a limited number of nuclei, but not all nuclei. And therefore, I encourage you to go to certain characteristic problems concerning NMR, and you would see that this number of nuclei is always specified for H1 because H1 spectrum is completely integrable, and therefore you will be able to make out for each and every signal that has originated in the NMR spectrum is contributed by how many nuclei of the proton type. However, this particular information will never be available to you for C13 spectra, because C13 spectra or C13 NMRs are not integrable for reasons we will come to ahead in our discussion in NMR spectroscopy. So what exactly this peak integration means is that once the NMR spectrum is recorded, it gives us the peak heights that are completely integrable, and the integration of these peaks tells us or gives us the total proton count in the molecule. And based on the relative integrations of individual peaks, we'll be able to identify how many protons contribute to a certain signal. And it is a very useful information with respect to NMR, and hence it helps us in structure elucidation in many ways. Towards the end, let's look at the factors that affect chemical shift, and a few of the factors which are very important in deciding how the chemical shifts will be varied for a certain nuclei in the molecule are majorly electronegativity of the atom that is connected to this particular nuclei, because that will affect the electron density or distribution around the nucleus. Hybridization of the atom will also play a major role, because hybridization indirectly will have an effect on electronegativity and thereby will affect the chemical shift values. There's also one other very important concept in NMR called as magnetic anisotropy. The magnetic equivalence versus chemical equivalence and the anisotropic properties we'll be covering in the upcoming video.